You ever wonder how Netflix just knows what movie you want to watch next? Or how your bank spots a bogus transaction in milliseconds? Well, the magic behind all of that really comes down to a few core ideas in machine learning. So today, we're going to pull back the curtain on these foundational algorithms and give you a real, intuitive guide to how they actually work.
So let's kick things off with a simple analogy. Think about teaching a kid to tell the difference between animals. You show them pictures, right? You say, this is a cat, this is a dog. And over time, they start to pick up on the patterns, the shape of the fur, the size of the ears, the sounds they make. Machine learning gives computers that exact same ability, not by us writing a million rules, but by letting them learn those patterns directly from the data.
Okay, so that analogy is a great way to think about it. But to really get a handle on these tools, we need to be a little more specific. So what is machine learning, really? Let's nail down the core concept we're going to be exploring. At its absolute heart, machine learning is all about this: teaching a machine to find patterns. It doesn't matter if it's in images, text, or numbers. The goal is always to learn from data you've already seen, so you can make smart predictions about brand new data you've never seen before. And that's a total game changer from traditional programming, where a person has to write every single rule by hand. Here, the machine starts to write its own. Now, machine learning is usually broken down into three main categories, or flavors. You've got supervised learning, which is like studying with an answer key. Then there's unsupervised learning, which is more like exploring a new world without a map. And finally, reinforcement learning, which is like learning to play a video game by getting points for good moves. For our purposes today, we're going to focus on the first two, because they're the bedrock of most of the applications you use every day.
All right, let's dive into the most common type you'll run into: supervised learning. We call this learning with a teacher for a reason. Just like in a classroom, we give the algorithm a whole bunch of data that already has the correct answers. Its job is just to figure out the rules that connect the questions to those answers.
Within supervised learning, you're usually doing one of two things. First, there's regression. That's when you're trying to predict a specific number, like the price of a house or tomorrow's temperature. Then you have classification, where you're trying to predict a category, like is this email spam or not spam? Or is this a picture of a cat or a dog? It's the same learning style, just for different kinds of questions.
So, the place everyone starts is with linear regression. It's beautiful because it's so simple. It just looks at your data and tries to find the one single straight line that best captures the relationship between your input, say the size of a house, and your output, which is its price. Yep, it's all about finding that line of best fit you probably remember from high school math.
And this is exactly what it's trying to do. You see all those data points? The algorithm's entire job is to figure out the perfect slope for that line. That's the m in the equation. And where the line should start on the vertical axis. That's the b. Once it locks in the best values for m and b, boom, you've got a predictive model. It's a fantastic starting point for any prediction problem.
Okay, now for an algorithm with a kind of tricky name: logistic regression. Now listen, even though it has regression in the name, this is actually our first classification algorithm. So instead of predicting a number, like a price, it predicts a probability, the chance that something belongs to a specific category. The perfect example is your spam filter. The model looks at a new email and calculates the probability that it's spam. If that probability crosses a certain line, say 50%, it automatically gets shoved into your junk folder. This is the go-to algorithm for pretty much any binary yes or no question, from medical diagnoses to deciding on credit risk.
All right, let's move on to one of the most intuitive algorithms out there: decision trees. This model is basically just a flowchart. It makes decisions by asking a series of simple yes or no questions. Is the person's income over $50,000? If yes, you go left. If no, you go right. And you keep doing that, branching down until you hit a final decision at the bottom.
You know, the real beauty of decision trees is how transparent they are. You can literally draw one out and follow the exact logic the model used to get to an answer. And in a world where explainable AI is becoming so important, that is a huge advantage. Plus, while they're pretty simple on their own, they are the building blocks for some of the most powerful algorithms we have.
And that brings us to a really powerful idea. If one tree is good, what if you could ask a whole forest of them for their opinion? Well, that's the core idea behind our next algorithm: the random forest.
A random forest builds hundreds or even thousands of slightly different decision trees. Each tree gets to see a slightly different piece of the data. Then, to make a prediction, it just lets them all vote on the final answer. This approach, this wisdom of the crowd thing, dramatically improves accuracy and makes the model way more reliable. It also helps prevent a really common problem called overfitting, which is basically when a model just memorizes the training data instead of actually learning the underlying patterns.
Next up, we've got support vector machines, or SVMs. So imagine you have a bunch of data points from two different groups, say red dots and blue dots. The SVM's job is to find the single best line that separates them. But here's the cool part. It doesn't just draw any line. It finds the one that creates the widest possible gap, or street, between the two groups.
And focusing on that wide margin is absolutely crucial. By creating the widest possible gap, the model becomes much more confident and is less likely to make a mistake when new data shows up near the boundary. This makes SVMs incredibly powerful, especially in really complex situations with tons of features, like in text analysis, where every single word can be its own feature.
Okay, let's totally shift gears. What happens when you have a mountain of data, but no labels, no right answers to learn from? You just want to find hidden structures inside it. Well, this is where unsupervised learning, our Explorer, comes into play.
The most famous unsupervised algorithm by far is k-means clustering. Think of it like a data detective. Its goal is super simple. Sort a messy pile of data into a specific number of groups, we call that number k, where the things in each group are as similar to each other as possible. A classic example is customer segmentation, finding natural groupings of your customers based on how they shop.
So how does it actually do this? Well, it's a pretty neat iterative process. First, you just randomly drop k starting points, or centers, into your data. Then, you assign every single data point to whichever center it's closest to. After that, you move each center to the average position of all the points that were just assigned to it, and you just repeat those last two steps over and over and over until the centers stop moving. It's a really elegant way to let groups just emerge naturally from the data.
Now, a quick word on another clustering method, hierarchical clustering. The great thing about this approach is that you don't have to decide how many clusters you're looking for ahead of time. Instead, it builds this awesome tree-like diagram that shows you how the data can be grouped at all these different levels. It's perfect for when you just want to explore the relationships in your data without making any big assumptions up front.
So, we've looked at a whole bunch of individual algorithms, but in the real world, they almost never work alone. The true power of machine learning really gets unlocked when you start combining these tools to build a complete system. Let's see how that comes together.
Let's imagine we're building a fraud detection system for a bank. You'd use a layered approach. You might start with a super fast logistic regression model to get a quick probability score for a transaction. To make it more accurate, you'd layer a powerful random forest on top of that. At the same time, you could have a k-means clustering model running in the background, constantly looking for new and weird patterns of behavior that might signal a new type of fraud. And finally, if a regulator asks why you blocked a transaction, you can pull out a simple, transparent decision tree to give them a clear, easy-to-understand reason.
And when you put these tools together, the result is truly transformative. It allows us to automate incredibly complex decisions at a massive scale. It lets us create systems that actually get smarter over time as they see more data. And it enables the kind of deep personalization that powers everything from your Netflix queue to the ads you see online.
So there you have it. Those are the foundational algorithms, the real workhorses of machine learning. They're the essential tools for anyone looking to pull insights out of data. The real question is, now that you have a map of the toolbox, what problems do you want to solve? What hidden patterns are you ready to go out and discover?